In this lesson, we're discussing applied optimization. Those are just word problems that require us to optimize a function. And optimizing a function is just finding minimum and maximum values of some function. So these are just real-world applications of the content, the ideas that we have been studying in earlier sections. In earlier sections, we often found the relative minimum or the relative maximum of some function, or if we were on a closed bounded interval, we would find absolute extrema, absolute maxes, and absolute mins. All of that is relevant here, but now we're starting with a word problem. So we have to identify the function that it is that's being optimized, and then we have to optimize it. So here's our first example. I think the strategy for solving these problems is best shown through examples. So I'm going to do a couple examples with you. So here's our first example. It says, an open box of maximum volume is to be made from a square piece of material, 24 inches on each side, by cutting equal squares from the corners and turning up the sides. Find the dimensions of the open box of maximum volume. So we read the problem, and the first thing that I would do, excuse me, is identify anything that's relevant to solving the problem here. Anything that sounds like math, we should probably write that down. We want to identify what we've been given and what we need to determine. Also, if sketching a picture might help, it's always a good idea to sketch a picture. So I think in this case they're telling us we've got a square piece of material and we're creating a box from it. I think it's appropriate to sketch a picture. So let's sketch a picture to help us visualize what we're doing. And then we'll read the problem statement again, looking for any pieces of information that are relevant to solving the problem. So first, we're told that we have an open box. So it's a rectangular box and it doesn't have a top. And we want to maximize the volume. I'm going to circle that because that tells us exactly what we're optimizing. And it's to be made from a square piece of material, 24 inches on each side. So we start with a square. And we're told that this dimension is 24 inches and this dimension is 24 inches. Okay? And it says an open box of maximum volume is to be made from a square piece of material, 24 inches on each side, by cutting equal squares from the corners. You're saying, what does that mean? Well, it means we're going to take out like a little square over here, and a little square over here, and a little square over here, and a square over here. I guess when they say equal squares, what they mean are squares of equal areas. And then we're going to turn up the sides. So after we cut out this little piece, and that little piece, and that little piece, and that little piece, we're going to fold this piece of paper up on all of the sides. And we've cut that piece out, and we cut that piece out, and that piece out, and that piece out. And when we do, we're going to get something that looks like this. And it's open, it doesn't have a top, so I'm drawing it with an open top. So you fold up the sides, and it looks like that. The question says, find the dimensions of the box of maximum volume. So the first thing we did was we sketched a picture. We've labeled everything here, and now we want to identify what's called the objective function. Our textbook calls this the primary equation. In my studies of optimization, the function that we're optimizing is called the objective function. So I'm going to use that term, objective function. But it's the same as the primary equation referred to in your textbook. So we want to identify the function that we're optimizing. And they're going to tell us somewhere in the problem statement. We see, oh, we're maximizing the volume. So I need to come up with a volume function. I need volume as a function of x. Well, the volume of this rectangular box can be found pretty easily as long as I keep in mind the dimensions that I started with. Okay, so here's the idea. We take out squares from the corners. We don't really know how big those squares are. All we know is that they're squares. I could take out squares like the ones in the picture that I've already drawn, or I could take out bigger squares. And I could take out a square that looks like that, and a square that looks like that, and a square that looks like that, and a square that looks like that. And then I could fold up the sides. Do you see that if I took out a bigger square, this side would be taller when I fold up the sides? It's going to be that tall when we fold up the sides. Okay, so keeping that in mind, okay, well, I need a volume as a function of x in general. So what's x? Well, x is some unknown. Let's go back to that version with the red squares in the corners. Let's say I'm trying to find the volume of this box. Well, the volume of that box is length times width times height. Actually, I don't think that picture is going to be very useful with all those blue lines on it now. Let's draw the volume, or that piece of paper over here. We're taking out the corners. But the problem is I really don't know how large that size is. I mean, this could be 1 inch, and I could take out 1 inch over here and 1 inch over here, and I'd be left with 22 inches for this side. Or I could take out 2 inches and 2 inches, and then I'd be left with 20 inches left for that side. So in general, I don't know how much I'm taking out, but I could just say I'm taking out x inches on that side and x inches on that side. And if that's x, this is x, and that's x, that's x, and that's x, that's x, and that's x. So I'm trying to find this volume as a function of x, the unknown, how big that corner is, the dimension of that one side. Well, that x, when I fold that piece up, like that becomes the height of my rectangular box. And we know volume is length times width times height, but I need those as functions of x in order to find volume as a function of x. So that's x and that's x. That's the height. Now the length and the width are going to be given by this dimension and this dimension. Question is, how do we find this length and this length if this length is x and that length is x? Well, I think the easiest way to think about it is to think about it for specific values of x. If x is 1, so I have a 1 inch piece that I've taken out over here and a 1 inch piece that I've taken out over here, 1 square inch and 1 square inch. If x is 1 and this is 24 inches long, well then I took out an inch and I took out an inch, so I'm left with 24 minus those 2 inches, so I'd be left with 22 inches. If x is 2, then I've got 2 inches on this side and 2 inches on this side. So I've got the 24, and then this side would be length 24 minus the 4 inches that I took off. So in general, this distance from here to here, which becomes this distance from here to here when we fold up the sides, is 24 inches minus that x minus that x. So it's 24 minus 2x. And since this is a square piece of paper, this is also 24 minus 2x inches. So I've got 24 minus 2x inches over here is one dimension, and another dimension is also 24 minus 2x. So we identified the objective function, the function to be optimized. We've realized it was volume. And then the next thing we had to do was we had to write this volume as a function of a single variable. We're in Calculus 1, so we can only optimize functions of one variable at this point. When you get to Calculus 3, you'll be able to optimize functions of two variables. But for right now, we need this to be a function of one variable, and it is. It can be written as a function of one variable. The volume of that box depends on how big that piece is that we cut out of the corners. Question is, how many square inches is that? What's x? If I know x, then I know the volume of the box. So the volume of the box is just length times width times height. Length and width are the same, and the height is x. So we've got 24 minus 2x times 24 minus 2x. And we're multiplying by x. So you could call that 24 minus 2x quantity squared times x if you prefer. I'd probably write it that way. Or you can write this twice in FOIL and distribute in the x. Okay. Now the question asks us to maximize the volume. So we sketched a picture, we identified the function we're maximizing, volume, and then we wrote it as a function of a single variable, and now we just find the maximum of this. And you can use either the first derivative test or the second derivative test. Either one is fine. Okay. I think I would rather than using the product rule and the chain rule for this, I think I would rather distribute. So I'll call this, we've got 24 times 24 there. What's that? 144 times 4. So it's 576. And then outer times outer is negative 48x. Inner times inner is another negative 48x. So that's negative 96x. And last times last is 4x squared. I guess I could have factored out a 2 from both of those. 2 from this and 2 from this. So all this is divisible by 4. That's okay. And then we'll distribute the x in. And I think I will write it in the reverse order and factor out the 4. Oops, there's an x missing. There we go. Okay, so this is our volume function simplified. And now I want to find the maximum volume. So we're going to find the maximum volume using the first derivative test or the second derivative test. Either one is fine. But the first thing we always do, is we take the derivative and we set it equal to 0 to find the critical points. Okay. Bring the 4 down, and the derivative of x cubed is 3x squared. The derivative of 24x squared, we bring the 2 down, that's 48, times x to the first. And the derivative of this constant times x, just our constant. And I see that all of these have a factor of 3 in common, so we could factor out a 3. 4 times the 3 is 12. So I think this is 12 times 12, so 12 times 4 times 3, I factored out a 3. It's going to be 48. Okay, 12 times 4. All right, so we're here, and we want to set this equal to 0 and solve for x. So I need two numbers that multiply to give me 48, that add to negative 16. Since the product is positive and the sum is negative, the two numbers have to be negative numbers. A negative times a negative would be a positive, and a negative plus a negative would give me a negative. So 1 and 48 could be my numbers if they were both negative, but they don't add to negative 16, so that's not going to work. Let's try 2 and 24. Do they add to 16? Nope. 3 and 16. Do they add to 16? No. Okay, 4 and 12. Okay, they add to 16. So negative 4 and negative 12 will work. So we get v prime equals x minus 4 times x minus 12. And then we'll set this equal to 0 and solve for x. If this times this times this equals 0, that means one of the factors is 0. And then we just add 4 to both sides, or we add 12 to both sides. We get x equals 4. Oops, sorry, it's off the screen. X equals 4 or x equals 12. Okay, those are our critical points. Remember, we don't want, but the critical points do not necessarily correspond to the maximum volume. We need to make sure that, or we need to figure out which one of these, if there is one of these, that gives us a maximum volume. We need to figure out which one corresponds to a maximum volume, rather than a minimum volume. We don't want to accidentally minimize the volume when we intended to maximize it. So at this point, you've got some options. You can either use the first derivative test or the second derivative test. The first derivative test is pretty easy. You can just make a sign chart, or you could compute the second derivative of this. Also pretty easy. Plug in these x values and make a chart, and then use concavity to determine whether the critical points correspond to mins or maxes. I think I want to do both, just so that we can practice doing both. So let's make a sign chart for v prime. V prime is 12 times x minus 4 times x minus 12. Now, if this were just a regular problem, my number line would go from negative infinity to infinity. So I'd be saying x can be any number between negative infinity and infinity. But that actually doesn't make sense for our problem. Look at this. Look at this piece of paper. X is a side length cut out of a piece of paper with a 24-inch side. So x, as being a side length, it has to be positive. So x is going to have to be greater than 0. So I don't need any of those negative numbers. And if I'm cutting out a corner from this side, and this is 24 inches, well, x definitely can't be 12, because if x was 12, I'd have 12 over here and 12 over here, and I wouldn't have much of a volume at all. So I think another reasonable bound is x equals 12. If x was 0, we didn't cut out anything, then we had no sides to fold up, and we have no volume. If x is 12, well, we cut out everything, and we have like nothing left, and we have no volume. But somewhere in here we would have a volume. X equals 4 is in between 0 and 12. And x equals 12 was a critical point of our volume function, but we're not concerned about what happens to the right of 12 because x can't be greater than 12. So we just need to see this x equals 4. Does it correspond to a minimum value or a maximum value of the original volume function? To figure that out, I'll make a sign chart. I'll look at the factors of v prime, which are 12, x minus 4, and x minus 12, on the two intervals that make sense for our problem. 12 is positive all the time. Excuse me. If x is a number between 0 and 4, let's say 3, if you substitute that in here, 3 minus 4 is negative 1. If you substitute in x equals 3 to this factor, we have 3 minus 12, it's negative 9. So v prime is a positive times a negative, which makes it positive. Now, if x is between 4 and 12, let's say x is 5, we have 5 minus 4 is 1, that's positive. And if x is 5, 5 minus 12 is negative 7, so that's negative. So we have a positive times a negative, that's negative. So what does that tell us? Well, it tells us that, well, if v prime is positive, that tells us that the original function for volume is increasing. Because remember, the derivative tells us, or the sign of the derivative tells us whether the function is increasing or decreasing. If the derivative is positive, all the slopes on the graph are positive, so that function is going up. If the derivative is negative, all the slopes on the graph on that interval are negative, so the function is going down. So I think we can see it goes from positive slopes to 0 slopes to negative slopes. We're going to be at the top here. At the top, well, that's a relative max, and that's what we wanted. We wanted to maximize the volume, so that's very good. We just found out that we will have a relative maximum at x equals 4. So v of 4, excuse me, which is 24 minus 2 times 4 squared times 4. So we took out these 4-inch corners, 4-inch by 4-inch corners, and then what was left was 16 inches. So the maximum volume is 16 squared times 4, so 1,024 inches cubed. And just to visualize that, I'm going to say this is 16. This is 4 inches, and this is 4 inches. This dimension is also 16 inches. And we've got an open box that looks like that. And remember how this started. It started as a piece of paper that looked like this. I have not drawn it to scale. Not consistent with that picture, sorry. But if this is 24 inches across, we said that's 16 inches. Let's take out a 4-inch by 4-inch corner from each of these pieces, from each of these corners here. Then what's left is something that is 16 inches by 16 inches. So it's 16 by 16, and then when you fold up the sides, because you've cut these pieces out, you fold up like this side, and then this side, and then that side. It's going to look like that. Okay, now, did we answer the question? I don't think we did. It says, find the dimensions of the open box of maximum volume. And let's outline our method a little bit better. Okay, what did we do? We started by reading the problem statement, and then using everything that was stated in the problem to sketch a picture. Okay, so we sketched a picture. And then we identified the objective function. That's the function that we're trying to minimize or maximize. And it's going to be told to you somewhere in here. It's going to say maximize this. Find the maximum volume, find the maximum area, find the minimum length, something like that. It'll be stated here somewhere. I saw an open box of maximum volume. It says, I said to myself, I'm going to maximize the volume. So identified that. And then we need to write that function as a function of a single variable. I wrote volume as a function of x. It's possible that in some of these problems you're going to have a function of several variables. Like volume could be a function of length and width and height. But that's not what I want. I'm in Calculus 1, not Calculus 3, and I can't have a function of 3 variables yet. So we need to write this volume as a function of a single variable. If it feels like you've got more variables than you need, you have too many variables, go back to the problem statement. There's something in here that will allow you to write this as a function of a single variable. So if you're starting out with a function of x and y, there's something in here, we call that a constraint equation, that tells you how x and y are related. We'll see that in another problem. Okay, so you write the objective function as a function of a single variable, and we did. And then we optimize the function. We're trying to find the maximum. So we said we can use either the first derivative test or the second derivative test. Now they both start the same way. You have to find the critical points. Those are possible x values of our minimum and maximum values of the volume function. So we compute the derivative, we set it equal to 0 and solve for x. Okay. And then I decided to use the first derivative test. Using the first derivative test, when using the first derivative test, we create a sign chart. Create a sign chart for the first derivative. And notice what we had to do with the domain. I could have made a sign chart with 4 intervals from -infinity to 0, 0 to 4, 4 to 12, and 12 to infinity. That's what I would have done if this was just f prime and I was optimizing some function of x that didn't mean anything. But in this case, this volume function meant something. This is the volume of a rectangular box, and x is a length. It's a little length that we're cutting out of a piece of paper. So the smallest length I could cut, or I could just choose not to cut at all, would be 0. It's possible to have a 0 length. It's just nothing, right? But you can't have negative length, so that doesn't make sense. So we needed to get rid of those x values in the domain that don't make sense for our problem. So we got rid of it. And then we also had to think about, okay, is it possible for x to be greater than 12? And actually, I wasn't thinking to myself, is it possible for x to be greater than 12? I was looking at this 24-inch piece of paper, and I was saying to myself, what is the largest that x could possibly be? Well, it's going to be that 24 inches divided in 2, because I could make x half of that and x the other half of that. We wouldn't have much left over. We wouldn't have any volume. So the largest x could possibly be, and even then we really wouldn't let x be that value, would be half of this distance, half of that length. Half of 24 is 12. So I knew that I really shouldn't consider any x values greater than 12, because I can't take out a 13-inch piece and a 13-inch piece from a piece of paper that's 24 inches in width. Okay, so we created a sign chart, and then we, I guess we need to restrict the domain to values that make sense for our application. And in this application, x is a length, so x has to be greater than 0, and because it's coming out of a 24-inch piece of paper, x has to be less than 12. We create a sign chart. We found a we determined that one of our critical points corresponded to a maximum, and that was the first derivative test. And then we found the maximum value. So we said v of 4, which is this, is the maximum value of v on the interval from 0 to 12. And if you're saying, what about at 0 and what about at 12? Well, look at this function. It goes from increasing to having a 0 slope to decreasing. I think at 0 and 12, those are definitely going to be less than that maximum in between. We don't have a lot of hills and valleys. We just have the one hill. So that's the maximum value of the function on the closed interval. The other option, which we didn't follow, was to use the second derivative test. You'd say, okay, and then this was just drawing pictures and making sense of our answer, making sure we truly understood what it was that we were doing. Okay, second derivative test. Once you found that restricted domain, once you realized that the domain was between 0 and 12, you could say, okay, let's take my critical value and substitute it into the second derivative. This is another option. Rather than doing the first derivative test, you could have done this. V prime was 12 times x squared minus 16x plus 48. And the second derivative is just the derivative of that. You bring the 12 down, and then you multiply by the derivative of x squared. The derivative of x squared is 2 times x to the first. And now I've got a constant times x here. The derivative of a constant times x is just my constant. Derivative of 48 is 0. So this is v double prime. If you want, you could factor out another 2. 2 times that 12 will give me a 24. And so you see v double prime is that. Now, in order to use the second derivative test, what we do is first find the critical points. Remember, critical points, we found them back here. Those correspond to when the derivative of the function is 0. Critical points may also correspond to x values where the derivative is undefined. We didn't have any in this case though because v was a polynomial. But again, remember what it is you're looking for. Even though it's not clear here that that's what you're looking for, this is it. You're looking for those places where the derivative is 0. And remember, the derivative is 0 when the tangent line is horizontal. So you're looking for the x values where this happens. If you're at one of these points, you might be at a relative max or you might be at a relative min. So we found those x values. They happened to be 4 and 12, and then 12 was on the end point of our sort of realistic domain. So x equals 4 is really the only critical point that we're interested in. If I want to test x equals 4, if I want to determine if we have a max or a min there, I can evaluate the second derivative at 4. 4 minus 8 is negative, times 24, still negative. So second derivative is negative. Now remember what that means. That means the graph is concave downward. If the first derivative at 4 is 0, and the graph is concave downward, then you must be at a relative max. So that's at x equals 4. So that means v of 4, which we already calculated earlier, is 1,000, oops, there's an extra comma there, 1,024 inches cubed is a relative maximum. Okay, so you use the first derivative test or the second derivative test to determine whether you've got a relative max or a relative min. We used the first derivative test and determined we had a relative max. We could also have used the second derivative test and said, hey, look, we still have a relative max. Either way, we're going to get the same answer. And then the last thing we do is we make sure we answered the question that they asked us. This one says, find the dimensions of the open box of maximum volume. So if somebody asked you for the dimensions of the open box of maximum volume, and you said 1,024 inches cubed, you would be wrong because you didn't answer their question. So make sure you answer the question asked. I know sometimes I'll tell students that and they kind of roll their eyes. They're like, of course I answer the question asked, Miss Townsend. I'm telling you because a lot of people don't. A lot of people make this mistake and they just tell me v of 4, or they just say x equals 4 is the answer, but it's not. We want the dimensions of the box of maximum volume. When x equals 4, we take out 4 and 4 from this 24-inch side. This side length is 16. And that means this side length is 16. So we've got a 16 by 16 by 4 inch open box. Those are the dimensions. That is the answer to the question that they asked. So make sure you answer the question that they asked. That's the last step. So we'll say the dimensions of the box of maximum volume are 16 inches by 16 inches by 4 inches. And we're done. Okay, so that's pretty much how it works. Sketch a picture, identify the function you're optimizing, write it as a function of a single variable, optimize it. You can use the first derivative test or the second derivative test, but remember the first thing you do is find the critical points. Now this is a really important step. Make sure that you restrict the domain to the values that actually make sense for your application problem. And then after you've done that, after you've optimized the function, you found the maximum or the minimum, make sure you answer the question that they asked you. If they asked for maximum volume, you could say this. If they asked for dimensions, you could say that. If they asked for both, give them both. But whatever it is, make sure that you answer the question that they asked you. Okay, so that's our first application, and I think I'm going to save the second example for another video.